In this video, we're going to look at electric field for distributed charge a little bit more, kind of continuing where we left off. You can look in your packet, page 16, 17, 18, those pages as well, and we'll, kind of post this stuff. But specifically, we want to look at some more complicated distributions, a ring of charge. We've already looked at an arc. What happens if it's a disk of charge and so on. The steps we're going to use is we first convert our vector sum of electric fields into a scalar integral. Then we substitute for dq into some sort of a spatial variable. We figure out how to, what the limits of integration need to be, and then we actually do that. So this is on page 18. I think it's labeled as example 4, if I got everything correct. So we have a thin insulating ring. Insulating just means we put the charge there and it can't move. Which is nice. A uniform negative charge is given to us. We have a radius of 10 centimeters and a charge density of theta equals -2 times 10 to the -8 coulombs per meter. Point P is along the central axis, a distance x from the center of that ring. So we want to know, what is the electric field at that point? So there's a couple of pieces we need to do. One thing, just as an aside, if you could ask yourself, what is the electric field at the center of that ring? And the answer to that is 0, because essentially a shell theorem, or a version of it, is occurring there, right? No matter where you are, the electric field is pointing at the little bit of dq radially outward, and all of those have an equal and opposite piece that cancels out. So once you get to the center, you should be at 0. And that means as you go outward, it'll change as well. There actually is a maximum point, but we'll get to all that. So we know that the electric field is defined as the integral of dE. So the first thing we need to do is think about that. Here's a little dq, my little red square there, and there's my dE pointing toward it along that r, lowercase r distance. Right? And we form a nice little triangle here, and we're going to use this triangle. The base of that triangle is x, the distance along the axis. The hypotenuse of the triangle is little r, and actually the height of that triangle as you go around is capital R. So you've got a nice, it's actually a constant for a given problem like this, which makes our lives a little simpler. So the y components of this will be the ones that are different every time, or you could think about them as the z component, whatever you want, kind of the components that diverge up, down, left, and right as you spin around. They will all cancel out via symmetry. So only the components along the x-axis are going to survive. And if we look at that little triangle, the components that are along the x-axis would be those that are determined by the sine of theta, I believe. No, sorry, the cosine of theta again, because the sine of theta would be the pieces along, kind of up and down. If we take that, then we could say, here's our electric field is equal to d integral of dE cosine of theta. The dE, as always, becomes k dq over r squared. The lowercase r is the distance that we need between the point P and the bit of dq. And we need to do our substitution for dq. Since it's going around a circle, we're going to use ds times lambda. And then we get to this spot where we have to decide, have we done enough substitution? Are any of these values constants? If so, what are they? I certainly want to have x in here somewhere, because that is the distance we are from the center, and we know that number. So we're going to have to think a little bit about what's going on here. We know that r squared, because this is a right triangle, is equal, little r squared is capital R squared plus capital X, or plus x squared. So we can do that substitution. And we then can define cosine of theta in terms of x, which is good, and r, because again, that angle theta is actually a constant in this scenario as we go around. So now we end up with this. We've got the integral of a bunch of stuff, k times lambda times x divided by 3/2 of r squared plus x squared. It's kind of convoluted and it's not intuitive. But then we have ds, and it turns out that all that other stuff is just a constant, right? X is a constant for this problem. Capital R is a constant, K is a constant, lambda is the charge density. So this integral actually simplifies down quite a bit to just be a bunch of constants times the integral of ds. And the integral of ds as you go around the whole circle is just the circumference of the circle. So we don't even have to actually compute an integral hardly. We don't have to do anything else. It's just 2 pi times capital R, because that's the radius of the circle. And from there, we have, some constants that we can get rid of. Lambda and times 2 pi r is just the total charge, right? That's the charge density times the circumference, or the total distance. And we now have something where we can plug in all of our values and get numerical answer. Unfortunately, my slide controls are hiding it. And that is the amount of electric field at that point. An interesting thing to do is to look at this and think about what happens as x gets small. When x becomes 0 here, right? We already know kind of what's gonna happen there. We also know that we can also see that as this collapses on itself, right? We could find a place where we have our maximum value of x, but that's another thing we could talk about. So we can talk about E at x equals 0 by symmetry. What is it when x is really, really big? Well, if x is really, really big, then the radius of the circle basically doesn't matter. And this just becomes kqx over x cubed, or kq over x squared. So the idea being, if you get really far away, it's just a point charge now, right? If you imagine going far and farther away, that little ring, it doesn't even look like a ring. It's just like a point a long distance away. Oops. So it looks like a point charge. And then, of course, the electric field approaches 0 when you get infinitely far away, right? If x becomes infinity, then the electric field is basically 0. So how would we figure out the maximum value? Well, the basic way to do this would be take the derivative with respect to x, set it to 0, and solve for x, because we know that's when we have a turning point, a change from positive to negative slope. This is maybe not the most trivial, derivative to compute, but you find out that the answer to this is r over root 2. That's when you get your maximum value. So basically, you go from 0 when you're inside up to a maximum value, then you go to 0 again when you're infinitely far away. From example 4, we can start with the answer for the electric field from a ring of charge, which we just calculated. But what about a disk of charge? Well, as we've learned before, a disk is basically just an arbitrarily large number of rings added together. And that's what we're going to do to figure this one out. So hold off on that for a moment. But I just want to point out there's a lot to this. You should be able to, and this is what you are expected to do on the AP exam, is use the integration, use the symmetry to figure out things like situations 2, 3, and 4, right? A line, an arc, and a ring. You are not expected to be able to do the tougher examples like 5 and 6. Example 6 is at the end of this slide deck, which you can look at with just a long line of, a line segment of charge, which is different than a line. And then we'll use a different method, Gauss's law, for highly symmetric kind of infinite arrangements of charge, which actually end up being kind of elegant and pretty. So how do we do example 5? Well, you start with that answer from the ring. And we think about, well, what are we actually changing here as we go from the middle outward? Well, if we are actually integrating this from a radius of 0, basically a point at the middle all the way out to the end, it's actually that capital R that becomes our variable, right? So we have k times x times dq as we have over all this, 3/2 stuff. We're just going to add up all these concentric rings. So dq in this case is now a surface charge density, a sigma, times a little bit of area. But what is that little bit of area? Well, the area actually is 2 pi r, the circumference of that circle, times dr, the thickness of that circle, and sigma is the total charge divided by the area of the big disk. So r, I'm changing it from capital R to a lowercase r, right? Because r is the radius, capital R is the radius of the whole disk. And we're going to go from the little r being 0 all the way out to capital R. We have to integrate this, which seems a little bit messy, but remember, x is actually a constant here. So we can break this up a little bit to solve it, distribute, and so on and so forth, right? Doesn't really matter. got a bunch of things. So what does all this mean, right? If I were to look at this, and I still do often look at it and go, well, what does it even mean that we have this sigma over 2 epsilon naught, which again, why I would make that substitution isn't obvious to you, times 1 minus x over the square root of r squared plus x squared. Well, the reason why I pause here and put it in this form is that we basically have constants times 1 minus a thing. And we can look at some extreme examples. So what if this plate of charge actually just kept growing and growing and growing and was so big that, or we were close enough to it, that it seemed to go on forever, that it was essentially infinite, which basically means that x was really, really small relative to capital R, or that R was really, really big with respect to x. Well, if that happens, then this whole term of x over the square root of r squared plus x squared just goes to 0. Because if r gets really big and x stays constant, that goes to 0. And this whole thing collapses down to electric field is sigma over 2 epsilon naught, which is a constant. And that makes sense because an infinite plane of charge, we already said, should provide a constant electric field. And that's exactly what this shows would happen if you were to let this disk keep growing and growing and growing until it was actually infinite in size. So this example is more about giving us a justification for why the electric field from an infinite distribution of charge on a plane or a very large plate is constant, and less about a technique that you actually have to use to solve problems. Okay. The big thing is that it doesn't depend on x. You can be as close to it as far away as you want. If the plate is actually infinite, the uniform electric field will always be there, no matter how close or far you go, left, right, etc. So what is an application of this? Well, we often, we can't actually make an infinite plate of charge, but what we can do is take 2 plates of charge and put them relatively close so the things moving in between them don't really know that it's not infinite, that it's your distance to the plates is small compared to the size of the plates. And you can actually do interesting things like this. And if you remember from chemistry about the discovery of, charge to mass ratio and the charge of an electron and the existence of electrons and protons and all these subatomic particles, you probably remember the Millikan oil drop experiment, which of course, gets Millikan's name because he was the guy who was running the lab and not because he probably did most of the work. Unfortunately, this is the reality of scientific history. But the elementary charge can be reasoned by doing an experiment where you take little droplets of oil, which is what he used, and they could fall through this hole. But as you squeeze them out, they become charged. They get an excess electron or 2 or 20 or some number. We know now that you can't have half an electron, right? We know that charge is quantized. And so that's what was found by the Millikan oil drop experiment. You could adjust the amount of charge on those plates by adjusting the voltage. We'll talk about that later in our study of electricity, how those two things relate. But what was found was that we always got a charge that was divisible by the same number, right? We got lots of different possible charges that we calculated, but they were always divisible by the same number. And to find that, you have to do a lot of trials. You have to do this over and over again, hundreds and thousands of times to get this data in a grouping where you go, oh, yeah, it's always an integer number of this particular number, which we now know is 1.6 times 10 to the negative 19 coulombs. An inkjet printer actually works this way. Many of you probably have an inkjet printer at home or have used one at some point. Laser printers use a different technique, but an inkjet printer basically shoots a tiny droplet of ink through something that causes it to be charged, a charged particle, and then there are plates that it travels through that have an electric field that can vary, and it will basically spray it onto different parts of the paper as it moves. There's also some physical movement, but this allows, in a pass to cover a small thing. I have these answers up here, but the sign of the charge of this drop has to be negative because it is deflected opposite the electric field. And this, again, looks a lot like projectile motion, that parabolic path. All right, that's it. Again, right after this is the example 6. If you're interested in looking at it, you don't have to. Not in the video. I'm not going to go through it, but it is in the set of slides.